Hello everybody, and welcome to this second seminar of the Security and Cryptography module. Today we will continue the transition from cryptography to security, and we will cover the next level of cryptographic operations, in particular those related to digital signatures, digital certificates, and public key infrastructures. So in today's seminar slides, you can follow the following couple of chapters from Goldman's book, but there is lots of other literature out there which covers these topics, so you can find a lot of other resources as well. Right, so we start with digital signatures. First of all, an explanation: what is a digital signature? Basically, a digital signature is the encryption of the hash of some data that can be then signed using the private key of the owner sending or performing that digital signature. So if you consider that M, for example, is the message that you want to sign, and you are Alice, for example, or A, that you own private key KPRA, then essentially a digital signature is written in the following form. Okay, so we apply the operation of signing using the private key for Alice to M. And this operation is denoted here or expressed as a curly bracket with a vertical bar. Okay, so this is in terms of the notation itself. However, in mechanical, or let's say computationally, or mechanically, let's say, how this sort of thing is done is expressed by the following diagram. Okay, so first of all, you have a message that you want to sign. Okay, so that's your message M. So you do three things. Okay, so the first thing you do is you hash that message, for example, using MD5 or any of the SHA hashing algorithms, and that produces a unique number corresponding to M. Okay, so this is what we call the hash of M. Once you've obtained that, you then take this hash and take your private key, okay, or the private key of any entity that is performing the signing, and then you use that private key to encrypt the hash of the message M. Okay, so we then obtain an encryption of the hash of this message M using the private key of the entity which is performing the signing. Now, once we've got that, you've got the signature, and all what you have to do is attach it or compose it with the original message. Okay, so note that the original message here remains clear, so we're not hiding it in any way. All what we're doing is that we're just simply signing the message. Okay, and the outcome of that, as I said, is expressed more kind of cleanly in this notation. Okay, that M is enclosed by these two brackets with vertical bars, and with it comes the private key KPR. So what does a digitally signed message tell us? It tells us two things. Okay, so the first thing, or the first property that we obtain from this, is that we know that the message has not been modified. Okay, and the second thing is that we should be able to know where the message came from. Okay, or what the origin of this message was. Now, these two properties are obtained through what we call the validation of a digital signature, or the verification of a digital signature, which essentially allows us to establish these two properties. Okay, so let's have a look through this diagram to see exactly how that validation or verification of a digital signature takes place. So the first thing you have is the signed message. Okay, so remember this is, or what we said is that a signed message is some kind of message, okay, which comes with this sort of encryption of a hash using private key. Now, the first thing we do in the in this validation process is that we extract this message that we've just received. Okay, so let's call this message M prime. So the first thing we do is that we extract M prime and put it aside. Okay, and this is very easy because you've got two things. All what you're doing here is you're picking one of those two things and putting it aside. Okay. So then we go on and hash this message M prime, and that obtains, and in that way we obtain its hash. Okay, so some kind of a number that corresponds to M prime. Okay, so we set that aside and we forget it for the moment. Okay, and at the same time we extract the signature itself, which is an encryption of the hash of the original message. We then take the public key that we believe corresponds to whoever we think would have signed this message. Okay, so we take that public key KPB and we use it to attempt to decrypt this encryption. Okay, so if we succeed, it means that the public key that we have selected matches the private key that was used for encryption, and therefore the decryption succeeds, and we're then able to extract the original hash that was generated before. Okay, so remember this is the hash. This hash here is the same hash that we obtained at this step initially when we were generating the digital signature. So we have now this hash. We've decrypted it successfully. So we arrive now at a point where we can ask ourselves the following question: is this hash that we've just decrypted equal to the hash of the message that came with the digital signature or not? If the answer to that is yes, i.e. that these two numbers are the same, then we've established that this message M here, which was the original message that was signed 2 slides ago, is indeed the same message M prime which we've just received with this digital signature. Okay, so this means that the two messages M and M prime are basically the same, or in other words, that the original message M was not modified when we received it. Okay, so we've basically received M. Okay, although we tend to call it here M prime because we want to allow for the possibility that that message is actually modified, in which case that will lead to us breaking this equality. Okay, so in other words, if M was modified during transition and you did receive something different M prime, then that would result in the hash of M prime being not equal to the hash of M. Okay, so in this case we've established a check on whether we can basically tell if M is modified in transition or if it stays faithful to the original message M that was originally signed at the source. But we've also established a second thing, which is through our ability to decrypt the signature, we've effectively said that whoever owns this key KPB is the person or the entity who generated this digital signature, because they have access to the private side of that key pair, and therefore it's only them who would have generated this encryption. Okay, so therefore through this process, we're able to establish the previous two properties, as we mentioned in the previous slide. Now, of course, in a more kind of meaningful way, this gives us two nice properties. The first thing is authenticity, so you're able to tell where something or where some kind of message comes from. And the second thing is accountability, because you're able to tell if that message was modified or not modified in transition. And that's precisely what a paper-based signature would do. Okay, so when you sign some contract, you're doing two things. You're first of all stating that the copy of this of that contract that you've signed, for example, is yours, so it comes from you. And the second thing is you're saying that this is the exact text that I'm signing. Okay, so any kind of modifications to that text will essentially lead to fraud, basically, or that is not the original. There are a couple of standards for digital signatures. So DSS, Open PGP are two widely used standards. You can, if you want more detail, you can follow these links and you can study these standards if you're interested in them. Of course, these are only standards, so they only specify how digital signatures should be produced and validated. But of course, there are also lots of tools out there. Some adhere to these two standards, some follow their own different method of signing and validating data. Okay, so far we made one important assumption, which was that whoever owns a public key really own it. Okay, so we kind of made some blind faith that if I told you that Alice owns KPB Alice, that indeed KPB Alice belongs to Alice. Okay, but this was just an assumption, a very big assumption, and so far we haven't looked at the problem of how this assumption can be sort of more assured through the mechanisms of cryptography. Okay, so and this is actually even more important when you consider the nature of numbers or keys. Sorry, that they are essentially just numbers. Okay, so if I give you a key, I mean even if in my notation I'm kind of specifying that this is the public key for Alice, but in reality Alice's public key could just look like something like this. Okay, so it's just a long number with absolutely no information in it to essentially indicate that it is a key owned by Alice. Okay, instead this ownership relation is established through something we call digital certificates. Digital certificates, basically all what they are is that they are a formal binding between a user, a machine, program, and the public key of that user. Okay, so they allow you to own a key, if that's the right word. Okay. Instead of just blindly believing that this key belongs to Alice or Bob or the server, you now have some kind of a mechanism to establish stronger trust that indeed this ownership relation is valid and correct. Now, in order for us to do that, we bring in something called certification authorities, okay, or CAs, and CAs will issue these digital certificates to basically bind users or machines or programs to their public keys. Right, so a digital certificate in the most simple form consists of these three categories of information. First of all, you have some information about the subject, i.e. the owner of the key or the alleged owner of the key. And then you have the actual public key for that subject, and finally these two categories of information are then sort of signed by this certification authority. The most sort of common format for certificates are X509 certificates. So these are again an IETF standard, which you can look through. It's a very lengthy standard, but what really matters here is just trying to understand these main sort of categories of information contained within the standard. In our notation, we will refer to a digital certificate in the following form. Okay, so first of all, we include inside a 5-element tuple, which consists of the certification authority's name or identity, the identity of the subject, for example, Alice or Bob, the validity period of the certificate, so the time stamp from which the certificate is valid, to another time stamp representing the end or the expiry date and time of the certificate, and finally the most important bit, of course, is the public key itself for Alice or the subject. Okay, so we have this sort of a 5-element tuple or information, and the whole thing, very importantly, the whole thing is signed by the certification authority. Okay, so it's signed by the private key for CA. Okay, so when it's signed by the private key for CA, essentially we are ending up here establishing that trust. Okay, the trust that Alice indeed owns this public key. Okay, so and the trust comes from the fact that we can see that the certification authority is essentially attesting to this ownership relation. Okay. Now that kind of again promotes what we call non-repudiation, or the inability to deny that a subject signed something. Okay, so if the subject was ever, for example, sending you a message accompanied a signed message, and that message was accompanied by their certificate, or even if it wasn't accompanied by the certificate, as long as you can obtain this certificate, you can then establish the fact that the subject did sign indeed that message, because with this certificate you can establish that they own the public key that can validate the signature on the message, and the signature, of course, would have been performed or generated using the private key for that subject. However, this raises yet another question. So the question is, now, do you trust the certification authority itself or not? Okay, so what we did basically here is that we just shifted the problem from this level to the next level, because you still need, in order for you to validate this certificate, you still need to validate the signature of the certification authority. Okay, and in order for you to do that, you need to be able to convince yourself that the public key that you're using to validate this signature is indeed the public key of the certification authority. So that raises another level for the problem, a level which essentially poses this question: can we trust that the CA, CA really owns its public key or not. Now, there are two options for us. First of all, we don't, and then we discard the original certificate that was linking Alice with her public key. That's one option. The other option would be no, we would like to move again yet to another layer upwards and try to establish some source of or some kind of trust for the certification authority itself. Okay, so this basically leads us to what's known as a public key infrastructure, which allows the building up of this trust across various hierarchies or various levels of the hierarchy. Okay, as we can see here in this diagram, you would start down here and you would move up to the next certification authority, and there may be lots of other layers as you go upward until finally you reach something known as a root CA. Okay, so a root CA, like Thwart, for example, these are companies that you can't go higher than these. So they are at the root of trust, let's say. Okay. If you want to see what root certificates look like, as I said, there is in this link there is some examples or lots of examples of such root certificates which are employed by by Google's Android operating system. So the process becomes like this. You basically, first of all, try to understand whether Alice or Bob own a key, and you do that by checking the certificate that was signed by the first certification authority level. If you are happy with that, that's fine. You proceed. If you're not, then you go to the next level, and so on. So you keep on moving upwards until you finally reached the root CA. Now, of course, you could dismiss the whole thing if you don't trust the root CA. You can say, well, I don't trust Thwart, and therefore I'm going to dismiss the whole chain of trust, and I don't accept that Alice or Bob own this specific public key. However, on a more positive note, you hopefully will at some point here in the chain hit certification authority that you will trust, and then you kind of convince yourself that indeed Alice or Bob own this particular public key. So the higher we're going up the chain, what we're doing is we're building up trust. Okay, so we're building up trust upwards. Okay. So as I said, when you reach the root, you encounter a trust bootstrapping problem. Okay, so in other words, who certifies the root? No one certifies the root because they are, by their definition, at the root of the whole thing or the whole chain. So in that case, you will have what's known as self-signed certificates. Okay, so these root organizations issue certificates that they sign themselves, which attest to their ownership of their public keys. Okay, and that will allow you to bootstrap trust, and there is unfortunately no other way around this. Okay. So that was the kind of X509/PKI model of trust. However, there is another one which assumes more kind of a flat landscape, and that's the pretty good privacy or PGPs model of trust. So the idea of PGPs model of trust, or sometimes known as web of trust, is that you trust whoever you want to trust. So you can imagine this as being a peer-to-peer system. There is no hierarchy. There's no hierarchy. There's no root, and you essentially have a set of entities that you trust, so you have their own self-signed certificates, and so if you were, for example, receiving some kind of a signed message and you wanted to retrieve the public key, you have no problem there, because the public key, as soon as you've got an accompanying certificate with it, you will immediately trust it. Okay. And for those that you don't trust, you simply don't keep the self-signed certificates in your database or system. So that's quite a different sort of model of trust than the X509 slash PKI. Now, from time to time, certificates could be revoked, and generally systems or data servers would keep a list of such revoked certificates. There are various reasons for those revocations. It could be that the user has left the organization they were working for, or perhaps a machine has been retired and it's no more in use. And therefore you want to revoke the certificate that belongs to that machine. Generally, organizations or systems or departments maintain what's known as a certificate revocation list. Okay, so this is like a blacklist containing all the bad let's say certificates. Okay, so the certificates that have been revoked. So one example could look like this. So you have here the serial number of the certificate and the date on which that certificate was revoked. Okay, so you might have some other information as well, like the reason for revocation and so on. But generally, that's the minimum kind of amount of metadata you would have for such a CRL. And what you would then have is a server in your department or in the region where you can basically submit the serial number for a certificate, and if you get a yes, then that means that the certificate has been indeed revoked. So you shouldn't, at that point, you shouldn't proceed any further. You should just stop, or kind of end your chain of trust, or don't proceed any further. On the other hand, if the answer is no, it means no, it hasn't been revoked, so you're all good to go and good to continue building up your chain of trust if that's what you're doing. Okay. So thank you very much for listening. Goodbye.